Hello, 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 testing. Okay, maybe we could start first. Then when people come, we'll do some announcement later. Right. So, I think over the weekend, Kendall asked this question to me. That's right. And converges, then 1 over an converge to diverge to infinity. Does this make sense? Is this true? Do you think? Right. If you take smaller number and then you take reciprocal, it will become bigger and bigger. Okay. So how to prove this? Well, so you just write down the definition. Okay. So similarly, when you do exam, also do like this. Okay, write down the definition. Okay, what do you want to show? So diverge to infinity means what? For every m in n, there exists a n such that for all n greater than n, for all small n greater than capital N here, imply that 1 over n will be greater than m. Is it correct? Is this the right definition? Okay. But if you notice this, this is really similar with 1 over m. Sorry. So an less than 1 over n. Right. Okay. But then this is an less than some 1 over m or 1 over n. This part here. This one look familiar. No? Your sequence is smaller than 1 over n. Oh, sorry. Yeah. Familiar? Familiar. No? Okay. So if not familiar, you write down the assumption condition again. Right. So what's the assumption condition? So we want to show for all, right? Okay, so let's fix some m n. Then we consider epsilon to be 1 over m. Okay, so by assumption, let's call this a new convergence, converge to 0 of an. Okay, from here, there exists an n in n such that for little n greater than n implies that actually an, because an is positive, right? So this is absolute an. And then because an converges, right? It means that absolute value of an minus 0 is less than epsilon. But then this epsilon we choose to be 1 over m. Okay, so we are done. Okay, so here is an greater than 0, and then here is an converge to 0. Okay, now. Okay, so in this course, sometimes you can use word, okay, but then I encourage you to use this kind of epsilon delta language, okay, to show limit, convergence, continuity. Later on, we'll learn differentiability, integrability. Okay, so all these try to use epsilon language, right? Okay, yeah. OK 吗？好吗，慧姐？周末过得好吗？啊weekend 啊，OK，呀，哎，你请假是吗？你要跟我讲哦，因为我不知道你请假。 我好像在系统才看到你请假，比较好啊，不然的话我以为你失踪掉，已经请假了。对对对，你可以给我通知我一下啦，就是呀，不是想一定要给我报告吧的，因为我以为你没有来，等看到系统我原来你请假。OK，嗯，right. Any question so far? Okay. If no question, then so I got the plan. The plan is how about this Friday? We make it into a revision tutorial. So I will go through important concept. Definitely is related to your exam one, lah. And then I'll release tutorial 6 solution earlier so that you can do first. And then if any more question, we can discuss like tutorial to tutorial 6 in Friday as well. And then yeah, what do you think? Does it work? Okay. Okay. Then I'll release tutorial 6 solution first. I think where's Chung Xian? Chung Xian not here. Maybe I will post Chung Xian solution also on tutorial 2. Yeah, so his solution is pretty good. So I will share to you. Okay, right. In that case, we'll continue with the content this week. Hopefully, we can get to differentiability this week. Okay, so let's talk about limit points now. So let's talk about some motivation example. Right, let's look at this function. Fx equals to sine. Okay, um, well, so my claim is this is continuous everywhere. Except 0. Okay, except 0. Why? Because 1 over 0 is not defined. Okay. So, and it's not defined 0. Okay, but if it's not defined on 0, right, we still can see what is the behavior there. Okay, so it still can see the behavior around 0. So meaning I just care about what happens near 0. Okay, sine curve is something like this one. Squeezed between -1. Okay, so although we don't know what happened here, but we can see what's nearby there. Alright, this is the idea of limit. Okay, so well, um, but if you consider two sequence, right? So maybe I consider this sequence here. Okay, that converge to 0, and then the other sequence that converge to 0 as well. Convince yourself that this sequence converges to 0. Is it okay? Because n in the denominator, so n get greater, this number gets smaller. Okay, so why I do this? So try and evaluate this. Let's see what do you get. Yeah, try evaluate this. What do you get? What do you get? One is a shift of -3 2 pi. The other shift from power. What do you get for this two? 2 pi. 2n pi. Oh, okay, thank you. Yeah, so one is forgetting n, the other one is forgetting pi. Okay, what's your sign formula? I mean, like, you know how to read this? This is an addition of multiple pi, 2 pi, right? Addition of 2 pi. So your sine is period 2 pi, right? Okay, the usual sign. Okay. Sine at minus pi over 3. Sine at minus pi over 2 is what? No idea. E. Okay. I think you should know the basic shape, right? Okay, so here's 0, here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi, right? Okay, but you can extend this, right? Repeat it. Okay, so at minus pi over 2, you get minus 1. At minus 3 pi over 2, you get 1. Okay, and then you evaluate the multiple of them. Okay, yeah. Okay, here is minus pi. Okay, so so if you have minus 2 pi over 2, you get 1. You add another 2 pi. Where's 2 pi? Here, right? You also get 1, and then 2 pi, you get 1, 2 pi, you get 1, 2 pi, you get 1. Does it make sense? Okay. And then you evaluate minus pi over 2, you get minus 1, and then you add a 2 pi, you still get minus 1. You add another 2 pi, you still get minus 1. Okay. So the first sequence you always get 1, the other sequence you always get minus 1. So what does it mean here? You take a different sequence that converts to 0, and these two sequences is a different sequence is the value of their value have different sequence. Okay. So what do you expect this picture to look like? So the picture actually look like this. Actually look like this. So you always attain minus 1, you always attain 1 at those points. Similarly, for all the other points in between 1 and minus 1. Okay. So in this case here, we see a band, right? A band of interval from 0 to 1. Here, where we see a band here. Okay, that get arbitrarily close to x equals 0. Not converging to any. Because if you still remember, if we want to make some function continuous, right? What's the idea? So if it is not defined here, but if it is defined anywhere else, we can just fill this point in. Okay, to make it continuous. But then we can't really fill a line here, right? I cannot say x equals 0, fx is interval. Cannot. Because what is function? You send one point to a unique point. Or you cannot send to a multiple point. Actually, if you go further in mathematics, this is something what we call topologist sine curve. Or sometimes we have a pun for it, topologist sin curve. This curve has sin. You know what sin? Yes, S-I-N. You know what that? In, you know what that? S-I-N. 啊，跑到運動嚟講喎咧，不好，沒有錯，心是個罪，這個可有罪。為什麼有罪呢？If we're gonna like add in this limit, okay, later we'll call this a limit point, but then I mean it's a limit of some sequence, right? So those limit we will add it in. This function is not going to be a function, those points. But then later we'll introduce something called close. Make it close. Okay. Sure. Topology sine curve. Because the short form of sine is also SIN, right? No, SIN. Okay, the full word is SINE. Okay. Next is how about if we multiply x to it? Okay. What happens if we multiply x to it? What do you think? the point that are closer to 0, what happened to them? Just now you see the band like this, right? Okay, but then now I multiply the x to it. What happens when the x get very small? The value also get very small. Okay, so get squeezed. Squeeze. So how does the picture looks like? Look like this one. Get squeezed. And because your s is getting smaller, and so I get squeezed. I think you guys see this as a calculus example, right? You still remember? I think you are asked to show what's the limit. The limit, yeah, limit of this at the point 0. And then you use squeeze theorem because sign can be bound by 1 and -1. Okay, yeah. And then this function here still not defined as 0, you know. This function is still not defined as 0, you know, because there's still a 1 over x there. But then we can define separately. Okay, we can define piecewisely, saying that x equals 0, I take 0. Okay. In that case, we can make this function continuous. You can show it is continuous actually. Okay. Yeah. Although the original function doesn't define f at 0, but then you can throw in this point piecewisely. Okay, and then it matches up with the limit of your original function. Does it make sense? Okay. Okay. Question? Any question? Any question? 慧杰，懂讲梦吗？ Yeah. Okay. All right. So in this case, we'll call this a removable singularity. Okay. So originally, it's not defined there. Okay. It appears that 1 over 0 is a singularity. Okay. It's not defined there. But then if I define it at that point separately, okay, then this function, the new function will become continuous. Okay. Then we call it a removable singularity. Okay. That singularity we can remove. But the previously we cannot remove because it's impossible that we fill in all the limits at the point of the because you cannot say, oh, for x equals 0, I send it to the line. Cannot. Function cannot do that. Okay, function can only send to one element. Unless your call domain is built out of line, and there's a different story. But then here it's definitely not. Okay, it's just a real value function. Okay, good. So let's introduce this term here. So we look at so many limits of sequence. So we're going to define this. We say that C is a limit point. Let me see. Okay. Anyone still remember this notation? Domain of function is okay. Domain of function. Okay. If maybe I remind you, domain of f. If there exists a sequence Sn, okay, and then these Sn terms should live inside Df such that Xn not equal to C, and then for every n, but Sn converge to C. Okay, so maybe you will think that, hey, why I need to require this? Why do I need to require this? What do you think? Why I require that Xn is not equal to C before I talk about this conversion? Huh? That's FC, F, F. Not really doing with F yet. Not really about F yet. FC is not defined. We don't really care about F yet now. Yeah. Maybe you can think why Sn, when Sn can be equal to C, what could happen? If Sn equal to C, right, then every point will be a limit point. Every point in the local domain will be a limit point. in the domain, right? You just take a constant sequence. Then there will be quite trivial for this definition to appear, right? So we want, so meaning what? To be a limit point, you need to have someone else that get close to you. 明白我讲的吗？不明白 Okay. So if Sn equal to C, what's the if I allow Sn equal to C, can you find a sequence that converges to C? But but if Sn can be taken as C, then what's the sequence that converges to C? Can you give me a sequence that converges to C? C lah, constant C lah. Then every point basically is a limit point lah. Then this definition kind of trivial already. 不是讲不好啦，就没有太大用处了，对不对？So here we want that if you are a limit point, we want different point to get closer to you，对吗？是这样讲的哈，是这样讲啊。当一个人是这个群组的中心的时候，是因为有别人跟着。自己跟自己的时候，有没有人跟？他是比较中心啊？没有吃，我没有吃啊，就是随便吃吧，是不是？make sense 吗？对吧？明星的话，这边有很多人追着他，如果他自己唱自己的，就没有人理他，对吧？是这样讲吗？OK，limit point，OK，OK。So how do you use this limit point? Yeah. Okay. So before that, let me go through this slide. Okay. So since we introduced limit point, right, there's another point, okay, that related to limit point. So if C is a point of DF, which is not a limit point, so meaning there's no other, you cannot find a sequence, okay, that converge to it. What do you think? What happened to this point? 西安旁边那个叫什么？哦，你回答了，等一下，我想问一下他的意见。对，你叫什么？我忘记了，sorry。永俊，哎，洪俊，OK，对，洪俊，我一直记永顺是那个嘛，对不对？OK，洪俊，OK，洪俊，if 如果 if there's a point that there doesn't exist a sequence that converge to it，你觉得这个，哎，这么我把答案写出来，你觉得这个点是怎样的？没有人靠近它，不 continuous。我不知道你的 continuous 是什么意思啦，but then like 可以用另外一个词语来解释。没有点靠近它啊，没有人靠近你，你会怎样？你怎样？你哭，不要哭，不要哭。你怎样？你怎样啊？你就一个人哦，是不是一个人？对不对？OK，so this is what we call an isolated point. Isolated 知道吗？知道什么是 isolated 吗？What is it？隔离呀。OK，so you're isolated. It's like an island 啊，island isolated. Okay, so for example, EF equals to this. Okay, so what are the limit point? What are the isolated point here? What do you think? Given this set here. Okay, good. Okay, good. So how do you show that? So wait, let me see. Which one should we do first? Let's show isolated point first, and then we will show the closed thing later. Okay, we're going to show the closed. Okay, so let's show the isolated part first. So Y2 is an isolated point. How do you argue? Argue for definition, okay? So whenever what question asked in this course, you need to go back to definition. I say isolated point, okay, you go to dictionary, find what's isolated point. Okay, so if it is a point in DF, which is not a limit point, okay, so which is not a limit point, so you need to find what's limit point. Okay, go back, find what is limit point. So not a limit point means what? You need to take the negation, okay, negation of this statement here. So you should say that, say what? There does not exist a sequence such that if you take the sequence not equal to that point, then it doesn't converge. Okay, then it doesn't converge. Okay, doesn't converge. So what if you don't take 2 as your term of your sequence? Where can you pick your sequence from? Where can you pick your sequence from? Where? 我只发我要你讲出来。Where? 0 to 1, right? But then if you take any sequence from here, can converge or not? Can converge? Can or not? Can converge? Yes or no? And you need to make decision because I was gonna ask you to make decision in the exam. So you need to make your decision quick. Otherwise, you cannot finish my exam. Okay, yes or no? No. Okay, why? Why? Why no? Conversion, you need to go to dictionary or find out what is the definition of conversion. 品杰今天舒服吗？品杰还好啊。OK 好。So convergence doesn't converge means what? You need to find an epsilon such that what? Sn minus 2 cannot be less than epsilon. Okay, but then what epsilon you can take here? What epsilon you can take here? What epsilon you can take here? What epsilon can you take here? Huh? What epsilon can you take here? This number is always greater than. So basically, because this is positive, right? It's always greater than 2 minus 1, which is equals to 1. So your epsilon here, you cannot get closer here. Here, cannot get closer. No sequence. All the sequence were either at here, here, between 0 and 1. You cannot get very close. Does that make sense? Okay. But from this picture, can you see this 2 is also an isolated point? Can see or not? And see from the picture, it is isolated actually. 词汇可以从照片看出来它是 isolated，就记一个人是 OK, good. Okay, so how about let's show that the limit point of bracket 0, 1 is the closed interval. Yeah, let's show this. Or instead of showing this, maybe we show it for a general statement, which is show for open interval AB. Okay, we change the 0, 1 to any number in real number such that this interval makes sense. Okay, to do that, so let's do this. Let's do example first. So we're gonna show that maybe say all the limit points. All the limit point okay, so maybe I phrase like this. So the closed interval AB is all the limit point of the bracket A. Okay. Um. So how do we show this? So let's draw a picture again. Okay. So in this class, you cannot run away from picture. So A, B like that. So you got a round bracket. But then I'm gonna show that all the limit point live in the closed interval AB. Okay. So what do you need to do here? So meaning you need to check that every point in closed interval AB, you can show the limit point definition. But then if you go outside this AB here, they are not the limit point anymore. Okay, so you need to do two things. Okay, because you need to know where we are living in. Okay, so this is living in a real number here. Okay. Okay. So in this course, we will just deal with real numbers. So what to do here? So basically, maybe I rephrase it using set theory, so that we are sure we are doing here. So this closed interval here is equal to the limit point of bracket AB. Okay. Well, so you want to show set equality, right? So you need to show subset inclusion. Okay, left to right, right to left. So let's do this direction here. So this means that if I take point from closed interval, I want to show that S is a limit point of the closed interval AB. Okay, so basically I stated it 3 times here. Hopefully you know it. Okay, so well, you need to create sequence for me. Okay, you need to create sequence for me. For basically for every point inside there, right? Okay, so maybe there are 3 cases to think about. Okay, maybe 3 cases to think about. So for example, if x equals to a, can you create a sequence that live inside this interval that converge to a? Okay, if x equals to b, can you create one? Okay, so another case, I would just treat all the middle point the same case. So we're going to break one sequence that work for all. Okay, for A, what do you think? So you want to create something that gets closer to A. What's the thing that get closer to A? Okay, maybe you don't know how to get closer to A. Can you get closer to 0? 1/n, huh? Okay. Qiang favorite uh decreasing sequence. Okay, 1/n. Okay, 1/n is the easiest one. 1/n. Okay, basically you replace increasing function at the bottom, you can get to 0, but then yeah, diverge to 0 one, I guess. Okay, increasing and diverge. Okay, by the way, use 1/n, but then 1/n can converge to 0, right? Can it converge to A or not? What trick can you play? Plus A, lo? Okay, but then plus A got an issue here, right? You are not sure that whether A plus 1, for example, is inside this interval. So what can you do to it? How do you make sure that those points can live inside this interval?
1/n times b minus a dot b divided by.
Yeah, with 2. Okay, so we just take a plus b minus a over n. So meaning what? You instead of take 1 as your whole interval, you just take the distance here. Let me see. Let me check. Okay. 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 I think it's because of our open interval here. Uh, sure. Okay. So do you know which point is not in the domain? Maybe let me ask you. If I define like this, which point is not in the domain? Huh? X1, yes, when n equals to 1. So, um, so we divide by 2, huh? Sure, okay. So let's divide by 2. So in that case, the first place it occurs is b minus a over 2. Okay, and then you go down. Does it make sense? Okay, so and then you go down, go down, go down, go down, go down. Okay 吗 OK，有问题吗？没问题。OK。Everyone okay or not? This one converge to 0. And then this one converge to n. So this sequence converge to n. Limit law. Okay. Or you use the epsilon delta to show it. Okay, so this one converge to n. How about converge to b? Same trick, right? Okay, you can do b plus, but say，你一定要做决定啊，错不要紧，可以改吗？像我一样啊，不是改掉了，乘一个2就好了嘛，对不对？重点是人哦很坏哦，人就是很固执，他不要改了，你跟他讲错啊不改了，这个才是最严重的地方，错就要改，OK，不是错，最严重不是错，你知道吗？不是犯罪，是犯了罪啊，不要改了，不承认了，死活不承认了，OK，说你一定要改，OK，来，try B one B plus 什么？A minus B over 2. Okay, so why do you like swap the difference? Why not B minus A? It should be in the domain. Okay, very good. Okay, it should be in the domain. So how do you show that if this one is in the domain? 啊？什么 How do you show? How do you show? 上次不是教过你吗 How to show something living inside the interval? How to show? You want to make sure that this term is greater than A and less than B. Correct or not? Okay, so can you show it? Cannot, man? Okay, so maybe this one a bit long. Cannot show. Huh? Oh, okay. So I think we need to play the same trick again. Okay, two of them. Okay, can we show this? Cannot. So to show this, this is equivalent to do what? You take B away lah. This one is closed interval or open interval? Yeah, okay. So 0, then let me see. Did we do something wrong? 什么？I guess these SN need to pick from domain of F. So I think it's this right. This one need to pick from here. Let me think. Did I do something wrong here? Huh? SN is another. Yeah, sure. I mean, like I try to verify it, right? I want to make sure that this one is squeezed between N and B, right? Right. And then what did I do here? Minus 2 here. And this one gets smaller, right? Because this one is negative. What did I do wrong here? Oh, there's nothing wrong, right? Because A minus B is negative, right? So can we make this more obvious? Let me think. Can I make this more obvious? Okay, how about we change this to something that we know how to see? So let's say b minus a, I swap it, okay? And then maybe we can divide by b minus a. So, okay, and then this one just implies that 2n is greater than 1. But 2n definitely greater than 1 because we take n greater equals to 1. Okay, make sense? Okay, ma. So you see, you show something in the interval turns down to something that works in define your sequence. Yeah, no? So this is what I mean by showing. Does it make sense? Okay, ma. Okay, bye, ma. Okay. So again, this one by limit law should be easy to see also converge to B lah. So what is X then? X, random X, you just uh, take X plus B minus X over N. Okay. So you just treat closer A lah. Treat X as a closer. Okay, divide by 2 again because of our open interval thing. Okay, good. 没问题吗？大家没有问题，有问题问啊，我不会掩饰你的。也来题目哦，可以看一下题目，可以没有问题，没问题啊。Okay, good. Okay, right. So, how about the other direction? So the other direction will show that if it is not in this set here, then it is not a limit point. Okay, so well, there are two sides, right? If you look at the picture, okay, A, B here, there are two sides, okay. Well, I mean, we'll prove for one side, the other side is similar. Okay, we'll prove for one side, the other side is similar. So let's say there are two cases, and then we will prove them separately, but then the other will follow, I mean, similarly from the one. Okay, so let's prove for x less than a. So we'll prove this only where the other case is similar. Okay, well, so let's suppose for contradiction. So meaning that exists a sequence that converges to x. But then since x is less than a, then we just set epsilon to be a minus x. Okay, so meaning I have a x here. Okay, maybe use another color, this color. X here. Okay, then I set this as my epsilon. Can you find a point in your domain of not? Can or not? Okay, so if you set this distance here, we cannot find, okay, Sn in our domain. Our domain is open, right? Open AB such that absolute value of xn minus x is less than epsilon. No one inside here. Okay, no one inside here for you to pick. Okay, there's no one inside here. Why? Because all your points inside open interval AB. Does it make sense? Okay. Yeah, because you need to make sure your tail live inside here, but there's no point you can pick from. Make sense? 明白吗？可以给一点反应吗？摇头也可以。OK，点头。OK，一个人点头，摇头可以。有反应吗？你知道什么时候人没有反应吗？有没有人知道？哎，春先偷笑偷笑，什么时候人没有反应啊？春先啊，说说看，什么时候人没有反应啊？ ，sorry，吃掉死人啊啊哈，对对对，是这个是这个。只要你活着，你都是有防御的，你还要呼吸啊，对，应该是有防御的，反正死人是没有防御的。OK，手标做个活死人，呀，可以反应头摇头也可以。我不是神呢、对啊。
我有反应的话，只是你没有发现我会怪人。
哦，这样子讲话啊，哦，原来是这样，哦，原来是这样的逻辑，I see I see I see I see，顶级逻辑，这样就很惨哦，就是说，嗯、很长时候会大家不知道你要什么，然后你就在那边哭，很常小孩子是这样嘛，对不对？孩子哭哦，你不知道他中午，他妈妈会表手啊，肯定是饿的，然后给他测奶啊，but then 没有全部人都是你妈妈哦，我不是你妈妈，所以我不会知道你要什么东西。你哭可能你值得一直学。OK，我尽量啊，我尽量啊。But then，我不能保证我成为你们全部人的妈妈啊，对不对？对不对？所以，所以，所以什么意思呢？意思是什么呢？你觉得意思是什么啊？子晴，子晴，你知道你觉得意思是什么啊？我不能成为比全部人妈妈，but 你可以表达你的说法啊。那你不表达的时候，你就不要怪别人说没有听你讲哦，你明白吗？你就不要怪人家哦。有些人是这样的，他在前面还不要跟你讲了，然后在后面他就讲，哎呀，你看那个啊这个啊那个啊怎么讲的啦？反正你自己做了什么呢？你问了你自己，你自己做了吗？你什么都没有做，在意识上面做嘛。跟他讲，啊，什么叫意识上面做？意识上面反应吧。谁知道你意识在做什么，对吧？是不是这样讲？OK，你看，说如果你有什么东西要让人家知道，你讲出来嘛。啊，人家要听不要听那是另外一回事。反正你没有讲，就是你的问题。I think I think 古时候很多这种故事嘛，对不对？含冤而死啊，什么这样。反正那种是可能讲出来了啦，也没有人听。OK OK. So in this case here, so we're gonna define some new word here. Um, some new word or new term here. So the domain, or maybe a set lah. But now we just care about domain of F. It's called close if it contains all its limit point. Okay, so this one justifies why we call a closed interval close. Okay, so it contains all its limit point. Okay, so now I think you should have a better understanding of close already. Okay? Contain all the point. What are the points? 对吗？以前你们听到 close bounded interval 的时候是什么概念？好像把那个 A、B 包进去嘛，对不对？But then now we care about all the limit points. It's not just A, B. All the points inside there are important as well. Okay, so let's close. Okay, close interval. Yeah. Okay, contains all its limit point. All right. So maybe before we break, let's introduce some more result. Okay. So from here, we can define from this limit point here. Okay, if C is a limit point of DF, then we say that F has limit L at C. If you have a sequence converge to C, F S N also converge to L. Okay. Then in this case, we'll write down this limit. Okay, maybe it looks very familiar. This notation here looks very familiar. If I replace this S with N, right, it's just a conversion of sequence. But then what I do for here now is I define a convergence of function. Okay, it's different. Function. Here is a function. Okay, convergence of function. So I define two things for you. Convergence of sequence and convergence of function. Now is the convergence of function. Okay, so here these points are real number. Okay, sequence is also real number, but then it's discrete. Okay, n equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then now it's just some random convergence. Okay, so meaning what? So meaning what I do here? Actually, when I write down this notation, right, I define this notation for you. X go to C, X go to C, and then I define Fx goes to L. Okay, Fx go to L by using this limit notation. So did you, if you just focus on this notation here, did you see any sequence? No, no sequence here, no Sn anymore. Okay, so this definition actually works for all Sn that converge to C. Any one of them. Okay, so if you're gonna talk about lim Fs to L, you need to talk about random sequence that converge to C. Okay, we are not thinking about point that get closer to C, but then sequence first. Okay, so in this class, whenever we define limits, right, we always start with sequence. Okay, and then we go to, like, for example, continuity, right? We start from sequence and then we talk about epsilon delta, points that close to the point that you're interested in. Okay, so here we also do the same. Okay, we at first define using sequence first. You see, in this notation, there's no Sn. Did you notice? No Sn1. Okay, but then we define it as every sequence that converges to C we care about. And then we check what is Fs. All of them have to converge to the same point, so that we say that limit exists. Okay, ma? Understand? For example, like the example we started just now, the topology sine curve for this one. If you look at the sequence that converges to 0, I can create a two sequence that converge to 0, but then the FSN converge one of them to 1, one or 2 minus 1. Okay, then the limit doesn't exist. Okay, ma? Fine. Okay. Okay. Okay, good. Okay, and then similarly, what do you expect from here? What do you expect from here? You also expect something like limit law to happen. Okay, so limit law for function. Okay, you can try and do this as a exercise. Okay, limit law of function. So this property says what? Limit operator for function is also a linear operator. It's also linear. Okay, it's also linear. Okay, it's also linear because limit of a sum of a function is a sum of limit. Then sum limit of a product is a product of limits. And then limit of a scalar multiple is a scalar multiple of a limit. And then quotient. Right, so it's a linear operator. Okay. Maybe motivate one part, then we will take a break, then we'll prove this. So we will recover some important theorem that you know before, okay, from what we have defined here. So first of all, suppose f is a function on domain. If C is an isolated point of df, then f is continuous at C. I think this one is related to what Qian asked at first, right? What domain you can pick here? Okay, so if it's isolated point, then it's trivially continuous. Easily show it is continuous. If C is a limit point of df, which is in df, then f is continuous at C if and only if limit of fx exists and equals to fc. This is what you use in calculus, right? To show something is continuous. I think last sem I teach calculus one. I told them what's continuity. Your function is continuous whenever your value of f equals to the limit of f at that point. Then your function is continuous. For them, it is that. For you, what is it? Sequential continuity, epsilon delta continuity. Okay. And then next part, if C is a limit point of df, then
we have this limit. If and not if the function, okay, the function we define like this. So what's this function here? So we still take fx, okay, for dx that's not including the point C, but at C we take L. This function is what? Is continuous. Okay, so what does this mean here? So this means here, C is a limit point of df, right? This C might not live inside df. This is what we have seen just now, right? We show that the closed interval AB is a limit point for open interval AB. So meaning what? A and B are the limit point of open interval AB, but it's not in the open interval. So yeah. Any question? Hmm. Yeah, what question? Can ask.
I think it's continuous. That part you can add an additional two word at C.
At C, let me see.
The condition is control. I think the full function is
Correct. So I think, let me see. Let's see.
that part. Sometimes you write at C, or you can write at C.
Let me see. Oh, yeah, sure. Unless I say this function is a continuous function. Okay, sure. I think I can add a C.
At the other place, it just follows the continuity of f. If f is continuous at df, then the whole thing is continuous. Okay, but the point here is we make it continuous at C. Okay, this is similar to the removable singularity we see just now. Okay, we know the limit, and at that point in, then it will be continuous there.
Okay. So maybe we will come back for proof later. Let's take a break until 10:11. Meanwhile, I think you can try and sign in. I will open up the attendance. Does it work for you? Your apps not working? I think my side also not working. Okay, it's okay then. Um, 你们其他 midterm 几时啊？二26号、5号、26号，下个礼拜咯。OK，那你说什么群先？哦，这个日本 OK，4号，6月4号。哦，那个假期过后了啊，是吧？哦，有8号，哇，一个比一个迟。诶，不要 make sense 啊，一般。我想问一下你们呢，你们对那些 tutor 有 feedback 吗？可以跟我讲，来，他们做到怎么样啊？好啊，还是不好啊？还是什么啊？OK 吗？有帮助吗？你们觉得有啊？一恒讲有啊？我问你啊，我问你啊，你 OK 啊？你就 OK 了。其他的呢？如果没有的话，你要跟我讲哦，是我叫他们来啊，我请他们来。你知道他们是谁吗？Sorry 啊，senior 啊，他们是 senior，他们I think third year 吧，third year 也有一个是 master，还有3个 master，其中2个是来我第一年来的这边的时候，我教他们的，然后他们在这边读 master，呀，其他人呢？其他人没有讲话哦，不好是吗？那丢的啊，你自己私人聘请的呀，其他人呢还好，办公没有空诶，FIP 没有他们这个先开始，嗯，一年的 FIP 你们呀，OK 有什么 feedback 你要跟我讲啊，说可以跟他们讲，想帮更好地帮助你们。 也希望你们能够在这个课学得更好一点。Okay, before we start, everyone look at the revision notes that done by your classmate or not? 有人去看吗？ I already posted a few of them. Yeah, so feel free to give feedback if you found any typos or content is not accurate. Please let me know or let the person know so that they can fix it. So basically, I received few of them. But I think there's 1 week missing, but then that person a bit lost of contact. So I got 1, 2, 3, 4, 5, 6 disappear. Okay, 7, 8, 9, 10. Okay. 11, 12 is who? 11, 12. 你啦，你做了吗？还没有做，要考试哦，讲半天啊，有做吗？要做吗？好像是你跟雨涵是吗？好像你跟雨涵，呀，OK，能教吗？这个礼拜什么？你试试看，呀，试试看，呀，试试看，OK，at least 那 content 打出来了，拿其他再慢一点再补啊。反正我们好像到13了，呀，OK，13、14是谁啊？哦，你们两个啊，OK，哦，你们两个应该快耶，我觉得不会，我记得你们有三个不是用打的吗13可以先打出来，因为我们考到13，13可以先打出来，14可以再13可以 try 再打出来，so that 我们有 like everything for midterm 嘛。But 5 and 6 I think 我不能 guarantee 你啊，因为那个人 maybe 有问题，我会追一追啊，如果不能就没有了啊。But then 春先我会 share 你的 assignment two 啊，因为给你看一下，这个是我要的答案，回答的很好，所以我要那种写法，我会给你们看啊。怎么这样子说？更多，我会学，我会学，我会学。哦，and then 好像你们刚才有些人知道嘛，对不对？So this Friday, we will review important concept for midterm, and then assignment also, and then I'll release the tutorial 6 solution earlier so that you can try them first, and then we can go through them in class if you have question, and anything before it, tutorial 1 to tutorial 5, and assignment 1, assignment 2 also we can go through together. And any question, concept you still not sure, we can go through on Friday, okay, before the exam. Is it okay? Yeah. Helen, 玉涵跟你讲我们的 plan 了吗？他没 update 你？OK，等下你结束前你跟我找我一下结束。他没 update 你啊？我以为他会跟你讲。你们两个是一起考试，不是烦人？OK OK OK. So let's continue. Okay. So out of these three property, maybe we will just show one in class. What do you think? Which one you are more interested in? OK，举手。一，只要一。哎，sorry sorry，没有 show 到给你看。OK。So out of these three properties, right? Let's show one in this class. Okay. So which one? 只要一，可以举手。没有人举。好，sorry，什么？有没有人举？一个，OK 来一个。俊伟掉是俊伟吗？OK，good，我记对了。三，一个，哇，比较多人三诶。是吧？OK，let's do 三 then。OK，I will give you solution。OK，不要气馁，我有给答案，but then we'll just do three in class. Okay. If you want, we can do it in tutorial sometime also can. Yeah. Okay, let's do three. So let's do three then. Okay, actually three is shorter. Good. So let's copy this statement first. Okay, let's do this. Okay, so this is a if and only if statement, right? So we need to left and right. Let's go to right first. So what do we do here? Uh, I think something wrong with the order of the notes. Okay, so let's do this. So suppose that C is a limit point. Of df. And then what do you suppose? You want to show that f is continuous, right? C. So what does continuous as C means last time? Do you still remember? What do you want to show? Okay, what do you want to show? Okay, I want to show that f tilde is continuous and C. What's the definition of continuity for us? So we know sequential continuity, we have epsilon delta continuity, right? Which one is more useful here? Epsilon delta or sequential? Sequential, right? Why? Yeah, why? Why? Assumption. You need to talk about assumption. Always think about assumption. Yes, because we define the limit of function using sequence now. Right. Okay, so sequence match them. Okay, we use sequence. Okay, so what's the sequential property here? So for every Sn that converge to C, we want Fxn also converge to Fc. So here is F tilde, right? So what is F tilde C here? We define it to be L. Make sense? 对吗？
我是把 definition 写下来。
Okay. So, but you know the limit of Fx converge to L.
So for every xn converge to C, right? You apply that limit. You apply that limit. What's that limit of that function? Is that
For all the Sn that's not equals to C, that converge to C, we have F Xn converge to Fc. No, converge to L, sorry. Converge to L. So can we use it? Can we use it or not? Yes. So why?
yes?
But then this Sn here will be sometime equal to C, right? Could it be an issue there? What do you think? Could be an issue. There be an issue there. 会有问题吗？你觉得？
You still remember what kind of xn we consider in the linear function?
The Sn cannot be C.
But then this part here
Could be C sometimes. Could it be an issue? You can try and think about it. Could it be an issue or not? 会有问题吗？会有问题吗？会有问题吗？会有问题？为什么？Definition of F and then 继续 okay, F equals to L.
So maybe you should consider different kind of C that appearing in here. Maybe it's eventually constant, right? If it's eventually constant, it's like C towards the end, then it will definitely converge to F tilde CO, right? But then, can it be occurring infinitely many times, but then can it be infinitely many times, but then not eventually constant? Is it possible? Can appear infinitely many times, but not eventually constant. Can man?
Have such a thing. I could ask whether there exists such sequence.
That exists such sequence or not? Yeah, I must say that. If there exists, is there any like condition, like any contradiction? Hey,
I guess that the separate cases first one is we take a subsequence of this C. I mean, we take a subsequence that contains all of this C and another subsequence that doesn't have all this C, but the another subsequence that doesn't contain this C may not be a subsequence. Because it can be fine. Okay, what is it? It can be fine here.
Okay. So my problem here is this sequence here, right? Could be C sometimes because this is just some random sequence that converts. But then if you're gonna use that condition there, that Sn here, that Sn there cannot be equal to C. Okay, so to use that assumption, right, we need to deal with the term that equals. Make sense? Okay. So this sequence here, okay, this is a random sequence that converts to C. So it could be equal to C sometimes. But then if you're gonna use the assumption on limit of F, that sequence that converges to C cannot be C. Yeah. Okay. Got
The subsequence must be some.
So let's write down the claim first. Let's write down the claim first. So here is the claim. So we observed that limit as when to C of fx equals to L. Actually, if and only if limit of x equal to C f tilde x equals to L. Okay. Okay, since the two functions are the same for x not equal to C. Okay, so this is our claim. So let's see if this claim obvious or not. This is our claim. So they are equivalent. Why? Because they are the same function when x equals. Does this solve our problem or not? Huh? Okay, yeah.
Because if it's not eventually constant speed, then it is not actually does not have C. So
Not have C.
so we have infinite xn that is not C and infinite xn that is C. Then in this case, in this specific case, you can take two subsequences and then you can analyze the two subsequences.
The two subsequent should converge to C, right? If a sequence converges, all the subsequent should converge to the same thing. Yeah. 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 Yeah, Jinghan. Sorry? Epsilon delta? What's about epsilon delta here? So our issue here is about the Sn not equal to C. You know what's our issue here? Yeah.
它表示是哦，
What do you mean? Yeah. So our issue is Sn not equal to C. So why is it that delta coming here? What's it? Why is it delta? Yeah, we need to prove this. So how do you use?
Basically, what we mean is like assume delta definition, right? The condition you have zero less than absolute value of x minus c less than
Yeah.
delta. And in this case, because it is the absolute value must be greater than
No, we epsilon delta we define on continuity only. We didn't define on limit yet. So there's no epsilon delta for you to talk about. Right. There's no epsilon delta for you to talk about yet. Yeah, I haven't talked about continuity for this thing. This is just limit. Did you? Okay. Okay. Yeah. Okay. Right. So if you have infinitely many points of um, if you have infinitely many points, where am I talking about? Okay, if you have okay, for this part I think makes sense, right? For this part makes sense because we only care about x not equal to c. Okay, for this part should make sense. But then does this imply this or not? Does this Oh, I think we are missing something to help us. Okay. I think we can settle all the eventually constant whatever thing. Actually by part two. Okay, we can settle it by this one actually. So if I want to show something is continuous, right? You just show this exists and equals to MC. Because if we accept the claim just now, it will just say that the F tilde limit exists, and then we define it to be FC, F tilde C. Okay, then we settle. So I think the technicality that we mentioned just now have to go into part two. Yeah, actually part two is a longer proof. Jingwei just now wanted to see this, right? This one actually is a longer proof. I think the technicality will come into this one. Otherwise, for part three, right, we can just use these two conditions. Okay. You show that the limit exists, and then y is equal to fd because we define it to be this y is limit. Okay. Yeah, so actually part two is an interesting part. Then you should have a look. Okay, so in that case, we're not only going forward, we also go backward already. So actually, we prove both sides. Yeah. If and only if. Okay, yeah, because part two is a if and only. Okay, any question so far? Yeah, so the technicality just now we mentioned, I have to go to part two, I guess. Yeah, part two actually is a longer proof. Okay, any question? No question or not? No question? Okay, so if no question, then we're going to define a similar epsilon delta definition for limits. So we said that f has a limit L if for epsilon greater than 0, there exists a delta, okay, also depend on epsilon such that for all x in the domain of f, and the absolute value of x minus c is less than delta epsilon. But we have this part here. This thing have to be strictly greater than 0. Okay, then will implies that the absolute value of fx minus L is
less than epsilon. So it has a limit at, maybe I should say, at the point C. Okay, at the point C. Okay, so if you look at this, what's the difference between this and the continuity definition? What's the difference? What's the difference? Continuity, epsilon delta continuity. What's the difference here? Also got epsilon, also got delta. The distance between the point C with other point less than delta, and then fx minus L less than epsilon. But there's one extra thing here, right? This absolute value here we consider greater than 0. Meaning what? We don't really care about the point at C. Okay, it's like what we do for limit point. We don't care about the point at C. Limit is like that, huh? 看你的周围罢了，我没有看你那个点本身做什么。Okay, this is what we call a limit. Okay, just neighborhood around it. Okay, 旁边。Does it make sense? Okay. But then this will tell us about continuity, right? Just now I show you. Okay. If this limit exists and then equal to the value of the function, then this function should be continuous. Okay, then you recover the continuity. Okay. Okay. So maybe one thing you can show is similar to the epsilon delta that I show in class for you. Epsilon delta limit should be equivalent to the epsilon n limit. Okay, so this one we left as an exercise. Okay, similar to the what case? To the continuity case. Okay, it's similar. Okay, question? Any question? 有问题吗? Okay, so you see parallel things now. We define sequential continuity. Okay, maybe right here. We define sequential continuity. Okay, and then we introduce epsilon delta continuity. Okay, similarly, we define sequential limit. Okay, and then we introduce epsilon. Wait, let me see. What do we call? Why do I call it epsilon n? Epsilon delta limit. Okay, so sometimes we call this epsilon n for sequential. Yeah. Okay. Because I give you an epsilon, you need to find me an n. The other one is I give you an epsilon, you find me a delta. Okay, so these are all equivalent. Okay, makes sense. Okay, ma. Okay, so maybe now I want to train one of your thinking. When you see limit, you should think of sequences. Okay, you should think of sequences converge. Okay, and then after that, we go to epsilon delta. You will think of all the points that are very close to the limit point. Where all the points that are close to the limit. Okay, so from sequence, okay, convert to a thinking of a neighborhood. So if you have this kind of thinking, then next time you can go topology. Okay. So this is the end of analysis. The end of analysis is algebra. Okay. Yeah. And actually end of everything is algebra, because algebra talk about structure. Things that must have structure one. If you have a fixed formula, why do you have fixed formula? Why it always work like that? There must be some structure that govern this mathematical object. There must be some principle, some axiom. Yeah. Okay, good. Okay, so there are structure inside that govern these things. Okay, I think we are quite early. Good. Okay, so what's the next thing we did for limit of sequence? Do you still remember? What is the very important theorem we had? Or limit law? After limit law, what do you learn? Do you still remember? After limit law, what did you learn? You can go and search your notes if you can't recall. Okay, so it is the squeeze theorem. Okay, so we also have squeeze theorem for a function. So suppose P is a limit point of D, and suppose further that fx is less than or equal to gx, less than or equal to hx. So meaning gx is squeezed between f and d, such that we know the limit of fx and limit of hx. Then we will know the limit of the middle function. Okay, we will know the middle. So any idea? Do you know how to prove this? Do you know how to prove this? What is D? Sorry, maybe I say R. Okay, yes, good. So let D be a domain. So FGX. Yes, thank you. Okay. Cool. Okay. So any idea how to prove this? So there are two definitions we introduce just now, right? You can either use the sequence definition or you use the epsilon delta definition. If you use the sequence definition, it is really just the squeeze theorem for sequence. It's just really a squeeze theorem sequence condition. If you use the epsilon delta definition, then you need to find me you need to kind of use the triangle inequality to do it. Okay, any question on this one? Can try yourself, this proof. Is it okay? Try yourself. Yeah, very similar to the squeeze theorem for sequence. I would say either use squeeze theorem for sequence or similar proof as sequence squeeze theorem for sequence. Okay, either you prove it similarly as squeeze theorem or to use squeeze theorem for sequence to prove it. Okay. Any questions so far? No question? No question? Okay. So maybe we can talk about what's the difference between sequence of function, squeeze theorem of function and squeeze theorem for sequence. Okay. So what do you think? What's their differences? Maybe in terms of picture. Okay, so for sequence, right, these points are like discrete. Okay, these points are like discrete. Okay, but for function, okay, for function, if it's defined on open interval or closed interval, then you can imagine these lines get joined together. Okay, these lines get joined together. Okay, so they are really immoral, they are the same thing. Does it make sense? Okay, yeah. Okay. Okay, so these are the squeeze theorem. Okay, so let's go to next concept, which is uniform continuity. Okay, so what is uniform continuity? So definition, function f on the domain df is uniformly continuous if for every epsilon greater than 0, there is a delta greater than 0, such that for all xy in df, whenever x minus y less than delta, implies that fy minus fx is less than epsilon. Okay. Right.
So what's the difference here with normal usual continuity? What's the difference here? Also got epsilon, also got delta. For all x also got less than delta, less than epsilon also got. So what's the difference here? What's the difference here? What's the difference? Do you realize this one for all for two things? Previously for all only work for one thing. Should I bring it up? Maybe let's go and find it. Continuity or continuous. Maybe continuous. Continuous. To find the epsilon delta version. Yeah. Okay. Yes, yeah. Let's examine this definition more closely. Okay, so what's the difference between these two? Got the extra y here. Oh, because this is for all, right? So let's turn this for all also. So let's say continuous here. So maybe I can add OC. Okay, so here actually for OC can be placed outside. Okay, so what did you see here? I move this for OC. Let's say the C is Y. Okay. I move it. So okay, maybe not from everything in R, from DF only. So I move it into after the existence. So what does this mean here? This means that this existence here depend on epsilon, could also depend on C, actually. Okay, so this thing here maybe depend on two things. But then here, I put this C at the back. So meaning what? This epsilon, this delta here should work for all epsilon. Okay, so this delta here only depend on epsilon. Okay. Do you still remember we showed the example of x squared being continuous? Do you still remember? Inside that delta, right, there is x inside there. Okay, so meaning at different point, you will pick different delta. Okay, but for uniform continuity, this delta here, you cannot, expression of delta cannot include x, only have delta. I only have epsilon. Okay, then you are uniform continuity. Okay, so maybe I should give you some examples. Okay, so let me give you some examples. So AG fx equals to x squared is not uniformly continuous at R. Okay, not the delta we picked last time. Anyone still remember the delta we picked last time? There's one version is epsilon of square root what x plus what, something like that, right? You still remember the x squared examples? Okay, maybe I find it for you. Here, this one. Yeah, so this is one of the delta that we can pick. Okay, depend on x, or we can pick the very specific one like that. Okay, also depend on x. But then the claim is, if I change the domain, let's say to 0, 1, then it is uniformly continuous actually. Okay. So what do I need to do for uniform continuity? Fix epsilon greater than 0. Okay. Then what do I need to show?
I want to show that there exists a delta depend on epsilon such that for all xy, if so xy in my domain, if x minus y less than delta, this implies that x squared minus y squared will be less than epsilon. All right, this is my goal. Okay. So you try your working. Well, maybe I can split this into x plus y and x minus y, right? Okay.
So can I bound this without talking about x? Can I bound this without talking about x? Where's my x and y live in? Live in where? Come on. 0. Close interval 0, 1, right? So, okay, this term I can control with epsilon, right? But then this term is a bit tricky. But all your point is coming from 0 and 1. So x plus y, what's the greatest value? What's the greatest value? 2. Huh? 2.0. 没有，我没有理他。Okay, so note that for all point in 0, 1, the absolute value of x plus y should be less than or equal to 2. Okay, should be less than or equal to 2. So what delta I should pick? I just pick delta to be epsilon over 2. Okay, so that if I make my difference of x and y less than delta, then this term here, I could bound it by 2 times 2 times epsilon over 2, which is epsilon. Okay, as design. Okay or not? So what's the issue here? The issue here is if I fix a bounded interval, then I can control one of the factor easily. Okay, I can control one of the factor easily. So if you look at this, the picture of x squared, okay. So it says that if you look at the whole domain, okay, there's no one delta that can work for all epsilon. But then if you fix a bounded domain, then a closed and bounded domain, then you can use a delta that works for all epsilon. Does it make sense? Okay, ma? 明白吗? Okay, so do you understand what the uniform here means? 还是不懂? Okay, so the uniform here means what? This delta will work for all x. Okay, will work for all x. Okay, no matter what x you give me, I use the same delta. Yeah, uniform. 每个人穿一样的衣服，每个人穿一样的 delta 衣服。Okay 吗？ But if you look across the whole real line, right? 每个人不能够穿一样的衣服，不能 cannot. Okay, so if you look at this curve, why cannot? Why cannot? Because you can see that they are the way they increasing or the gradient is different, very different. Okay, it's increasing very fast actually. Okay, towards the larger end. So you cannot use the same delta that works. Does it make sense? 明白吗? Can you imagine or not? If I fix an epsilon here, the delta is getting smaller. If you fix epsilon other places, the delta is even smaller. So you cannot have a delta that works for all x. 明白吗? But then, if you fix a closed bounded domain, then you have control on all the points here. Okay, so you know the delta that can works for all epsilon. Yeah. Okay, sorry, I didn't say a delta that works for all epsilon, meaning epsilon the delta is fixed for all epsilon. I mean that epsilon only depend on epsilon. Sorry.
The delta only depend on epsilon. Yeah, this is what I mean. Okay, yep. Hmm.
If there is bounded, if
It is,
imagine that because like if it is differentiable, then its derivative is bounded.
let me think. Not really. Not really. As this, if it's differentiable, it exists. Just exists. You mean bounded? What? Who is bounded? Derivative is bounded. Just exists is enough. Exist. I mean, for differentiability, by definition, is existence of derivative. Not bounded. Bounded meaning you mean the set of derivative is bounded. Huh? Yeah. No need. It's just defined at each point is okay for differentiability. Unless you want to talk about other advanced property. But if you just talk about differentiability itself, existence is enough already. No need to care about uniformly continuous. Oh, you mean continuity with differentiability? Let me think. Oh, it's bounded. Bounded. Wait, bounded. Actually, there's something called a list shift. Yeah, I think so. Yeah, I think so. Yeah, I think so. Yeah, yeah, should be. Yeah. I think lift shift imply uniform continuity. Okay, I think we will see that later. We'll see that soon. Yeah, we'll see that soon. That's called lift shift actually. Lift shift. Yeah, bounded. Yes. Okay. What time is it? 10:53. Okay. I think we should. Okay. So maybe we'll stop here with this theorem here. Maybe we can do it next time. So what we have discovered is if f is a continuous function on a closed interval, closed bounded domain, then f is uniformly continuous. Okay, but I'm not talking about derivative here. So it's just a continuous plus a closed bounded interval, uniformly continuous. You can find a delta that doesn't depend on x. Good. Okay, we will prove this next time. Okay. So see you tomorrow. Okay, see you tomorrow.